This one is n11, this one is n12, this one is n13, this is n21, 2, 2, 2, 3. Okay. So you just plug in n 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 2, 3, 2, 3, 3. This equation. Okay. And compute this test statistic. So R is 1, R is 2, and R minus 1 is 1. C is 3, C minus 1 is 2. Okay. So the degree of freedom is degree of freedom is R minus 1 is 2. This example, test statistic. Plug in the number. Test statistic is 7 times. And p-value is 0.01. For test statistics, 7.8, 7 and chi-square distribution with degree of freedom 2. The p-value is 0.019. So it means it's unlikely that the tax reform opinion is independent of the income level. If you look at this data, can you see why the income level is not independent of the tax reform opinion? If you look at the low income level, the reform opinion is about the same, 182 and 154. Right? The tax reform opinion for and against, they're not that different, but if you are medium and high income level, people tend to vote for the tax reform opinion. This one, the proportion is about twice as much that vote for the tax reform opinion. But for low income people, like the feeling is like doesn't matter because I don't have anything for you to be done. So the tax reform opinion maybe maybe reduce the tax rate, something like that. So people with high income would prefer for the tax reform opinion. So the income level is not independent of the tax reform. So we see, for the summary, can use chi-square test to test for proportion, to test for multiple categories, proportion, to test for distribution, to test for independence of random variables. The last topic in this class is linear regression models. Which I have more time on for the class, but there's a lot of things about linear regression, but I try to pick the most important topics that you should know for linear regression in a couple classes. So first, I will talk about what is linear regression is about, how to create equation for quick equation for linear regression, and how to check if your model is correct or makes sense. Okay. You see the hypothesis testing about the regression coefficients. And last thing is a different kind of linear model called generalized linear model that we can use to fit account data. Because normal linear regression is based on the data that comes from normal distribution. But generalized linear model can be applied for data that does not come from normal distribution, like count data, number of counts for accidents during one period. And those kind of data is not normal. Suppose some distribution, you can use this generalized linear model to fit non-normal data. Now let's see our data set first. This one. So this data set in linear regression, we are interested in predicting some variable called response variable or output variable. In this data set, our response variable or output variable is viscosity. So viscosity is some property of fluid. That tell you how what is, I don't know the word in English. Viscosity is like certain kind of property of fluid. If you have high viscosity, then the fluid tend to flow more slowly. If you have small viscosity, the fluid will tend to flow faster. This is data from some manufacturing plant. Okay. So the viscosity of this substance depends on the temperature. Temperature into temperature during the operation process, and the amount of catalyst, another kind of substance that you mix into this substance. It's a catalyst feed. Catalyst feed is the substance that you facilitate the chemical reaction in the manufacturing process. So you want to predict the viscosity of this substance as the function of temperature, operating temperature, and catalyst feed rate. Okay. So this kind of modeling problem, you want to find a relationship between this viscosity and these two variables, and you want to predict. Given the value of temperature and this feed not in this table, what would be the output viscosity? So to answer that question, we can use a mathematical model that represents this data. So the model that we will discuss today is called the linear statistical model. So linear statistical model represent the output y as the linear sum of variables x1 to xp plus some noise epsilon. Okay. If you don't have this epsilon, then your model has nothing statistical. There is no random deterministic model. If you have this term epsilon, this one is a random variable, it's kind of random noise added to your data. So your output y become a random variable. That is, you cannot predict it exactly. If you don't have this term, then your y can be predicted exactly by knowing x. Okay. And this this one, mu y given x, this one is the average value of y. So if you have this model, then the the average value of y would be this term, because these are all the scalar numbers, but this one is a random variable epsilon. This beta, so you see this beta is called the coefficient of the regression model, beta 0 to beta p. So we use this notation, the pole, the thick beta, to represent a vector beta 0 or beta p. It's called regression coefficients, which are constant. So this in the model they are constant, but it's unknown. Right? They are unknown constants. Beta 0 to beta p are unknown constants. X1 to xp is a numeric predictors. We call it a predictors. So this, like this example, you have x1 and x2. You have two variables or two predictors. Sometimes we call it predictors or explanatory variables. You can use this or this, so we tend to use this one because it's shorter. Predictors. Or it can be some dummy variables. We'll talk about this in a moment. But in general, it's a numeric. It's a numeric variable. What if it's not numeric? What if it's a categorical variable? You have a x that is a categorical variable, like this one, like OS, Android, iOS, or male, female. You need to transform the variable to numeric. We will show how to do that later in the class. Coefficients beta and predictor x, beta xi. Okay, and this epsilon, this term has a normal distribution. This is the key to linear regression, this model. You can think of this epsilon as the random disturbance or residual, because when you add this term to your model, it makes your model, it explains some variation that you cannot explain by these predictors. Okay. And it has a normal distribution with zero mean and this variance sigma squared. Okay. This sigma squared is called the error variance or residual variance. If you look at this model, the reason, this is a very important point that when you say linear model, it's a linear in terms of the coefficient. It's not linear in terms of x. You can change this variable x to anything. You can change it to x1 squared, x1 cubed, or the log of x1, or square root of x, or whatever. But you still await some of the coefficients. So this model is linear in terms of the coefficients beta, not linear in terms of x. Okay. So if you have the model like this, if your model is y equals beta 0 plus log of beta 1 x. This one is not a linear model because you don't have your model is not linear in terms of the coefficients, or y equals to beta plus square root beta 1 x. this one linear or non-linear? So you can write as the root beta 1 defined by x. So this one is beta 1 plus beta 0 beta 1 prime and x prime, right? It's still linear. This one is linear. And you transform this into a sum. Okay. You cannot transform this into a product or two terms. No. So this one is not linear. This one is not linear. This one is. You can transform this into linear model. Okay. So this one is still linear. You have so each of these. If you look at this data set, you can these are y1, x11, x11, x12, x11, x21. It is y2, y3 to yn. Okay. And this is x1, x11, 12, x11, 21, x12, x22, x13, x1, x23, and so on. Okay. If you have a single predictor, you have beta 0 plus beta 1 x1. If your model contains only one predictor, we call it a simple regression. Okay. So because this one has a normal 0 with mean 0 and variance sigma squared. So your data yi must have we assume that it comes from the normal distribution with this mean beta 0 plus beta 1 xi and sigma squared. This is the model that we assume on our data. Okay. And we try to find what is the value of beta 0 and beta 1. That best fit our data, and we predict the value of y for an unknown value of, for a different value of x. Okay. So in this case, suppose this is your data point, the 2 point, okay. And this equation, beta 0 plus beta 1 x, is just this line, this blue line. So it's called a regression line. And the difference between this point, the data point, and this regression line will be your error, this one, epsilon. Okay. So when you use the linear regression model for prediction, what you predict, what you actually predict is the mean, right? Because when you plug in the value of x, you get beta 0 plus beta 1x, right? So what you predict is the value in this line that belongs to this line, which is the mean of y. So when you use linear regression to do prediction, you actually predict the mean of response. Okay. You do not predict the response itself, you predict the mean response. Okay. This is a point that you have to remember. You actually predict the mean of the y, not predict the actual y. Okay. Because y itself, y itself is actually a random variable, right? The best you can do is to find the confidence interval of y. But you want single value, single number out of the model. That would be the mean value of y. Now, this one is pretty simple for one variable. So in usual stat class, they will start with a simple regression and then extend to multiple regression. This is because we have not much time, then I will skip to advanced level to particle regression. Keynote crash on me. Okay. So the process, so given this data set, the process of deriving this unknown constant from the data set is called model fitting. So model fitting means you have the data and you have this equation and you find the coefficient. Okay, and this model fitting. This equation is called a model. It's called model. This is a model. Model fitting means you find the coefficients beta out of the data. It's called model fitting. Okay. So the technique that we use to do model fitting, first you must have equation first. Alright, must have equation first, and then you do the model fitting. The technique that we use to fit the model is called least square method. So least is smallest square is take the power of 2. So the question is what square of what? This is square and try to find the coefficients that minimize the difference between the actual response and the predicted mean response. Okay. This is the concept of least square method. Now let's say you have observation, so the assumption is the number of observation and all the number of observations must be greater than the number of predictors P. So if you have P is 1, P is the number of predictors. If P is 1, this is when P is 1. If you have one predictor, then you need to have at least 2 data points. You know why? Because if you have 1 data point, then you cannot fit this equation, right? Because you have 2 coefficients, so you need to have at least 2 data points. If you have 2 data points, then you will fit the straight line on the file. Your beta 1 and beta 2 will be in line that connect 2 points. Okay, that is the worst case. So in general, if you have P predictors, you must have at least P plus 1 observations. Okay, but preferably much more than that. And Sij is the observation of Xj. So in this notation, J will be the index for predictor. Okay, J is the index for predictor, and I is the index for the observation 1, 2, 3 to n. Okay. So your equation will be like this. For observation I, you will have yi equals beta 0 plus beta 1 x I1. So x I1 observation I for the first predictor. Observation I for the p predictor. Okay. You can just write it as a sum like this. If you are interested only the mean, so this because this is the error term, random variable. This term will be the mean response. So you will respond with this term. So the error, so you form the error. This one is the difference between the observation yi. Yi is the actual observation, and this one expectation of yi is this term. So the least square method try to find the coefficient beta that minimize the sum of square of this one. So you form the function. So this term, because this is yi is your observation. This expectation of yi is this which is a function of beta. So this term will be the function of beta. So if you take square and sum it for all from I to n and get this one. So just plug in y here and beta here. So this function is called the least square function. So it's just the error sum of square. So this one is an error, right? And sum of square error. We call it error sum of square or least square function. So once you have this equation, you want to find beta 0 to beta 1 to p that minimize. So you know x, right? So x is your predictor. So you know x, you know y. This one you know x, you know y. So you just differentiate this term so that you can find beta that minimize this sum. So instead of beta that make this term smallest will be the solution of the model fitting. Now let's say this is your data. The screen is too high. Okay. Suppose this is your x1, this is your x2, this is your y. Okay. Let's write this data into matrix form. This vector y is this column. Okay. This vector x, matrix x. This one is an x1. This one is one, and this one is x2. Okay. And the first column is all one. Okay. If you write the data like this, matrix x and this y, you can rewrite this matrix, this linear model. This one, you can write this equation. This one. You can write your linear model in matrix form like this. Y equals to x beta plus epsilon, where y is your observation. So y is observation 1 to n is a vector. Okay. And x, this x is the first column is 1, and then you have the data for first predictor, second predictor, and so on. This beta is a vector of coefficient, beta 1 to beta t, and epsilon is the beta of the error. So once you have, so this is a matrix formulation of the model from in observation. So your least square function L is a sum of square error. Can be written as this. This function L. It can be right? Written as in the base as by using this matrix representation like this one. So this notation is a transpose. So this term is just y subtract x times beta and transpose multiplied by y subtract x beta. And so you can try for this one. You can try for this. Because if you have vector of beta here, when you multiply x and beta, you will have beta 0 plus beta 1, 80, beta 2, 8. Right? Now we just do the matrix differentiation of this one. So you differentiate this matrix equation with respect to beta, okay? Because you want to find beta that minimize this equation. Okay? If you don't know the matrix differentiation, that's alright. Okay? Just look at this result. After you differentiate this one, then set it to 0 and solve for beta. If you differentiate this matrix and set it to 0, okay, you will get this equation or this one. You just move this one to the right side. So you get this equation x transpose x beta equals x transpose y. This is the after you differentiate this one and set it to 0. So this means if you use this beta, if you minimize the value of L, this error is multiple. So to find beta, you just inverse this one. You just inverse this one and multiply it on both sides. If you multiply the inverse of this term on both sides, it will cancel this term. So this term will be gone. So you get this equation. So your coefficients. So this one is a vector. That is the product of this matrix. This is a y, response y. And this whole thing is just we obtain it from the predictor data. So you can think of the coefficients as a weighted sum of y, of yi. So we get ourselves the coefficients beta now. So you can see that your coefficients can be derived from the data x and y. So now your fitted models become this one. Hat. So hat means as a fitted coefficient. If the value without hat is the actual unknown coefficient, if you put hat above, it means that is a fitted coefficient. So the fitted response, fitted mean response is just y x beta. So just plug in beta hat from this one. You will get this fitted response or predicted fitted response. Sorry, fitted mean response. Okay. So let's say you have this data set x and this is y. So everything is derived from x and y. This matrix x and y. So this is so your beta is x transpose x inverse x transpose y. So your x is here. This is your x. So x transpose x is this one. So you multiply these two matrices and get this one. And x transpose y. So it's this matrix transpose. So you know how to transpose matrix. Transpose, we don't have to transpose matrix. This is your matrix. Just split it like this. It will be a transpose of a matrix. Quick transpose. Alright, remember this. It's a matrix transpose. This one is x, right? If you flip like get this matrix. So this is x transpose y. Okay. X transpose x. So x transpose y is this one. So so you have to inverse this one first. So usually we use program, use software to do it. You not use, you not do hand calculation. It's too hard for you to do matrix inverse. Actually, you can do it upon 3 by 3. Like that. That would be too difficult for you. Okay, so x, you inverse this one and use some software. Or Excel or whatever that you are familiar with. Invert this one, multiply with this matrix, x transpose y. You will get beta. So this matrix is x transpose x inverse. This is x transpose y. So you multiply these two matrices together, so you get these coefficients beta 0, beta 1, and beta 2. So your fitted model is y equals to 1566, this one, plus this is your beta 0, this is beta 1, 7.62 x1, 8.58 to x2. So in Excel you can bring computer, you can bring computer to do example, to do this kind of calculation. All of you have computer, so you know how to use what kind of software do you use? Minitab. You use software to do some kind of matrix calculation. You know how to use Excel to do like matrix inverse. No? Okay, you better learn it. It's high school math, matrix inverse. Anyway, this is a Python code. Python code. Just give it for you in case you want to try. This one is for doing matrix inverse using NumPy module. If you don't know Python, that's fine. Just use Excel. Oops. Okay. So how do you know if this is a good model or not? So what you have to check is to look at the residuals. When you want to check if your model is good enough to explain the data, so your model should be able to explain. When we use model to explain the data, we say that the model must be able to explain the variation in the response. If the model can explain the variation, different value of the response, then your model has a good fit, has a quality of fit. So this case, like this one, this is your data is kind of linear, right? And has low variation. This one, your data is still linear. X is linear with Y, but you have some kind of little bit higher variation. This one, you have a linear relationship between X and Y, but your data has high variation. Okay. So in this case, you expect that your prediction, your model will contain lots of error, the variance of the error, high variance. So when we study the quality of fit in the regression model, we use something similar to the analysis of variance. So we write down something like this. This term, yi subtract y bar, is the deviation of observation from the grand mean. So this term explains how your data deviate from the average. Okay. This one explain how your data different from the predicted value out of the model. And this one, this term is the difference between the predicted value out of the model and the average. Okay. So this is so this y hat is a value that comes from your model. Okay. So this term, if you this is a function of I. Right? We have index I. If you square and sum them over index I, this term is called the total corrected sum of square or sum of square total. So it's a deviation, like overall deviation of the observation around the average. It's called total corrected sum of square. Corrected means you compute it around the mean. This is the beginning of corrected. So you correct it by the mean first, and then you square it. This total corrected sum of square or sum of square total is a sum of the sum of square regression. So this term is a deviation from the model value predicted by the model around the mean. This term is called the sum of square regression. This is the error due to from the mean due to the model. And this is the error between the model and the actual. So it's the error sum of square or sum of square error. NSE. So the meaning of this equation is the deviation of the observation around the mean is the sum of the deviation due to from the regression model plus the deviation due to the error. So suppose this is your data, this is your yi, and this is your y bar average. So the total sum of square measure the deviation of your data around the mean. It's the total sum of square. Regression sum of square measure the deviation of your model, a fitted model around the mean. This is the sum of square regression. So it tells you how the mean, how the fitted model different from the mean. Okay. And the error sum of square tells you how your data different from the regression model. This is the error sum of square. Okay. Just this one. This is just how to find the sum of square error from y and beta. And just skip this one. In case you want to implement it by manually. This is not a hard, that should be like approximation. I don't know how it gets like. So to measure the quality of fit, we can use this term called the R square. This single value of R is a correlation coefficient between the observed and predicted value. So if you find a correlation between this point, predicted value and observed value, the value from this correlation is R. So if you have a high value, so R is between 0 and 1. If you have high value of R, then predicted response is they correlate with the actual response. So this term R square is a ratio of regression sum of square divided by total sum of square. So you can think of R square is the proportion of variation explained by the regression model. This is a total variation, and this is the variation explained by the regression model. So if this term is close to 1, it means that the variation in the data mostly can be mostly explained by your regression model. Okay, that is your model has a good fit. You can write this R squared as the SST 1 subtract SST over SST. So when R squared is close to 1, it means your model explains most of the variation. So like you have data like this, and so this is a fitted model. So the variation of the mean or of the data around the mean can be explained by this regression model. If you have R squared close to 0, your model, this is your fitted model, explain nothing. That is, you can use the mean to explain this variation as well. That is, your model very poor in explaining the variation of the data response around the mean value. So when you have high R squared, you have your data looks like this. You have data like this, then you tend to have, when you fit the model, then you will see something like this in a model. You will have a model with very poor, very low R squared. Because your model, you will not explain any variation of data around the mean. Because your data is highly fluctuating. So there can be many things that cause this. Okay. Usually,